Okay, then we have the second speaker of the day. It's going to be Jonathan Weinberger, and the talk is going to be about the dependent Gödel fibration. Jonathan, take the stage.
Thank you, Ivan. So, yeah, I'm going to talk about the joint work with Davide Trotta and Valeria de Paiva. Both, I think, are also in the audience. So, hi to both of you. The starting point of this historically goes back to Gödel and his Dialectica interpretation, named after the philosophical journal that it has been published in. So this was a proof interpretation used for relative consistency proofs. And the overall pattern of the translation is as follows. We start with some formula phi, and we assign to it a new formula, phi superscript d, of the form there exists some x such that for all y, phi subscript d holds, where phi d is a quantifier-free formula. And this pattern is really what is kind of in the realm of category theory has a surprisingly often, recurs or occurs surprisingly often, and we will see some of this in a bit. So before getting into technicalities, let me introduce just the main results that I'm going to introduce. So I call this talk the dependent Gödel fibration, but really what we have done is we have looked at a variety of different kinds of fibrations, all named after logicians that admit a form of quantification. So fibrations in general, or fibrations with more structures, such as bifibrations or trifibrations, where you have these kind of transports along arrows, either covariantly or contravariantly. Those, you could argue, have somewhat of a sense of admitting a kind of quantification or transport, but maybe this is in general not so well behaved. And I'm really going to talk about some well-behaved notions in the sense that they satisfy laws, logical laws, or generalizations of these in the fibrational setting. So the central notion here is the notion of quantifier-free element. So there you can see the tie-in to the ideas of the Dialectica fibration that I mentioned, where we're interested in kind of obtaining quantifier-free formulas. So here we're interested in quantifier or transport-free or transport prime elements in the fibers of a fibration. And those are connected to completions in a various way. So there is a sense of fibered products and co-products in a fibration. And a first result that we obtained is that the fibrations that admit all the fibered products or co-products are free, so arise as precisely completions of some given fibrations, if and only if they admit enough quantifier-free elements, where it has to be clarified what that precisely means. There is another notion coming from proof theory, from Hilbert's epsilon and tau calculus, which are calculi for classical or intuitionistic first-order logic that also admit quantifier elimination by kind of adding in these epsilon and tau operators. And we have a sense of fibrations admitting these operators. And that's the case if and only if the fibration is complete with respect to sums or products, respectively, and every product and every element is actually co-product or product quantifier free. I'm sorry, I've forgotten the product case here, which is the one that would hold in the tau case. Then we also are interested as a kind of intermediate step between bicompleteness and the ultimate notion of dialectica fibration that we want to get to. Those are what we call the local Skolem fibration, and those are fibrations that first of all admit enough coproduct quantifier-free elements such that also those coproduct quantifier-free elements are stable under the product, and we have proven that they satisfy a law of Skolemization, not in the complete uniform sense of a natural isomorphism between functors, as one might hope for, but they satisfy this Skolemization locally or pointwisely. So I'll also to explain what that means. And finally, the kind of motivating, I guess, result of all of this is to basically characterize that being a dialectica fibration, which is a fibrational generalization of this dialectica interpretation by Gödel. So being a dialectica fibration is exactly characterized by what's called being a Gödel fibration, which essentially means we have a local Skolem fibration that also admits a kind of prenexation in some sense. So again, the overarching theme in these characterizations is that we have this dual view, or I shouldn't say dual, but we have kind of some more external viewpoint of a fibration as a completion or an iterated completion. So that's the external viewpoint. But this can be expressed by a more internal viewpoint, which is a kind of internal condition of completeness of a fibration, not by an external completion functor or monad, but by the existence of enough of these quantifier-free elements or closure properties thereof. Okay, so classically, this dialectica interpretation I mentioned in the beginning goes as follows. We assign to any phi these phi d's, phi to the d's, that kind of involve as the quantifier free part the phi subscript d's, and the interpretation, well, that's how it goes. So inductively, by mutual induction, we can define these two d operations on the formulas. But what I want to put the focus on is how implication translates. So the image of implication takes the following shape. There exists some uy such that for all x and b, phi d of x, y implies psi d of ux, v. And the intuition behind this is that the newly introduced function capital U assigns to any witness x of phi lower d a witness u of psi lower d. And the new function y that we have here assigns to any counterexample v to psi to any counterexample v to psi a counterexample y to phi. And this implicative part is really what motivates the construction of what is known as Dialectica category. So this is due to Valeria de Paiva from the late 80s in her PhD thesis, where she categorified Gödel's translation, Gödel's proof translation, by defining a dialectica construction on the level of categories. So I'm going to sketch what that looks like in a second. There have been several variations of this involving monoidal structures on the underlying category. And those are particularly interesting because they yield models of linear logic. Later on, there have been generalizations to the context of fibrations and toposes. So the fibrational work in particular is important to our work due to Hyland, Beering, Hofstra, von Glen, and Moss. And also by Schulman, there has been a polycategorical version of the Dialectica construction, and there's a lot more work kind of following this pattern. In particular, these Dialectica constructions have seen a surgence in applied category theory and also other parts of logic that I've outlined here. In particular, in 2022, we had the AMS Math Research Community on Applied Category Theory, where Valeria mentored a project on Dialectica constructions, of which I was very lucky to have been a part of. So some resources can be found in the Topos Institute blog, which Valeria is affiliated with, and also in the special session of the JMM Joint Math meeting from last year, where a couple of group members presented our project results. So in those photos, you can see our groups or a subgroup thereof. And in particular, I was in a subgroup together with Matteo Capucci, Bruno Gavranovic, Abdullah Malik, and Francisco Rios, where we kind of gave a unified view for optics, lenses, and Dialectica fibrations. So optics and lenses are also known to some folks in the applied math, applied category theory community, and in theoretical computer science. And there's going to be an upcoming talk at the MFPS conference this year. So there has been some previous work by Trotta, Spadetto, and Paiva, who showed that in the case of simple products and co-products, which are like non-dependent, so in the kind of type theoretical terminology, non-dependent sums and products, these Dialectica fibrations coincide with what's called Gödel fibrations. And in the work that I'm talking about today, we're generalizing this work to, first of all, the dependent case, where we're talking about dependent sums and dependent products, not just Cartesian products or simple non-dependent functions. And we're also, in general, working towards a fixed class of what's called display maps in the base category. So that's kind of conceptually more of a technicality or a kind of convenient setup to achieve a certain level of generality. But whenever I'm talking about these display categories, you can conveniently also ignore them if it's just about the basic notions. And I should also point out that these quantifier-free objects that have played a role in this preliminary work already, they have also appeared in work by Jonas Frey, where he called them exists prime elements. Okay, so just to kind of illustrate what this generalization consists of, instead of just product projections, Cartesian product projections of this form, we work with now general maps from some object U to some object X, which you should think of as type families U of X modeled by, indexed by a base type X. And what we will be dealing with in the sort of fibrational picture is really with a tri-fibration. So we will be looking at Grothendieck fibrations that have this kind of co-Cartesian transport, which logically speaking is like reindexing, and they have both the left adjoint which acts like existential quantification or dependent sum, but we also have a right adjoint, which acts like universal quantification or dependent product type. So classically, the Dialectica categories, due to Valeria de Paiva, they have as objects. So here I'm already talking about the dependent case. They have as objects arrows from U to X, which are like these type families that I just explained. And then they also come with the propositional part, which is a mono into the kind of total object of this map, so into the domain of this map. And you should think of these objects as kind of standing in for formulas of the form there exists some X from here, such that for all U from here, the proposition alpha of XU holds. And the morphisms are maybe a bit complicated at first sight, though they consist of 3 stages. So first of all, we have a map in the base from X to Y, F0. Then we have a map F1 from this pullback to U, which in the type theoretic notation, it really models implication of a reindexing of V to U. And now if you maybe don't remember, but if you believe me that this is what Gödel's translation for implication looked like, in the upper stage for the for the propositional part, we have an arrow like this, which in the type theoretic notation looks like this implication here, and that's really the translation of what Gödel did. So as I said earlier, we want to work all the time with respect to a class of display maps, just because it's more general, but we can kind of forget about this now, so I won't really mention this. So now the fibrational version of Dialectica, it derives itself from what the Dialectica categories are, except now there's kind of one more layer of dependency, which is everything is indexed over yet another arrow in the, or another object in the base, and consequently for the morphisms, another arrow in the base that we're adding here. And also these alphas and betas, they're now just elements in the fiber. So they could be monos in certain instances, but in general, they will just be elements in the fibers. Okay, and so from this, I mean, kind of classically, it's known how to cover the classical Dialectica categories from Dialectica fibrations of a specific form. And the Dialectica fibration is bicomplete in the sense that it admits both fibered products and co-products, and it actually arises as an iterated completion, but not a simultaneous bicompletion. So, and how this looks like, we'll get to see in a second. So first, let's make this more precise. So we say, given a Grothendieck fibration P, we say that it has fibered or internal co-products if the fibration is also an op fibration. So the reindexing has a left adjoint, and this satisfies the Beck-Chevalier condition, which basically says that this left adjoint is compatible with reindexing. So it's like saying existential quantification coheres with reindexing. And of particular interest will be what's called the family fibration. So that arises as the pullback of the pullback of a fibration of the domain fibration of the base, and then post-composing this with the codomain fibration of the base, we get the family fibration sigma of P. So its objects are just arrows in B, but together with an object over the domain. And that also basically tells you what the morphism should look like. And what's peculiar about this is that it's the free co-Cartesian fibration on any given functor. But if the given functor is already a Cartesian fibration, it's the free completion. So it's the free completion of a fibration by fibered coproducts. Well, there is the kind of prime case of what's called the discrete or the set index family fibration of a given category, which basically motivates this construction and the notion of fiber coproduct. So we will also need fiber products. So first of all, in the base, those kind of come from Cartesian or locally Cartesian closed categories. So we say that well, we start with a map. Let's see. I guess there's some. There's some typo here. So the U should really be an F, and this should really be a G. So a dependent product of an arrow F along an arrow G is given by an arrow H like this, and an arrow E from the pullback, which is like the co-unit of the usual exponential, satisfying a universal property with respect to other diagrams of the same shape. And this also, an abstraction of this also serves to define what are fibered products of a fibration. You can also define them kind of dually to fibered products using the fibered the fiber-wise opposite of a fibration, but I won't go into the details of that. And then one can show, which classically has been done, or can be found in various works, for instance, in the very nice paper by Hofstra, Dialectica monad and its cousins, that the dialectica fibration arises as the iterated completion of first taking the fiber product completion of a fibration and then the fibered sum completion. So this is what completeness is about. Now I want to turn to the quantifier-free elements and their connections to completions. So the intuition from logic is the following. A formula alpha can be shown to be quantifier-free if the following kind of universal proof theoretic characterization holds. If we have a proof phi of a statement, there exists I of beta I under the assumption that alpha holds, then there exists a witness T, which depends on the proof pi, together with the proof of beta of this instance T. And that should satisfy these proofs should satisfy a certain kind of coherence condition. Furthermore, quantifier-free elements should be substitution invariant, and we should have a covering property, namely that every formula can be equivalently expressed by a quantifier-free formula introducing some new terms. And this has been categorified by Spadetto, Trotta, and the Paiva, of which we're presenting now a dependent, like a dependent generalization. And this also, I should point out, bears some resemblance or generalization of the notion of decomposable object in a complete category due to Carboni Vitale. So I don't want to go much into detail here because it's quite technical, but it's essentially a categorification of what I said before. So we say an object alpha in the fiber of a fibration that is fibered co-complete is called a quantifier like everything now is with respect to the fiber sum quantifier. So it's a quantifier splitting if for every beta in some other fiber, and for every vertical map from alpha to the co-Cartesian transport for every arrow u, there uniquely exists a section G of u in the base and a vertical arrow from alpha to the reindexing of beta in to the reindexing of beta along this section, such that we can decompose our original vertical arrow like this. So this is essentially the kind of coherence condition for these proofs that I mentioned before. And this eta here, that's the unit of the adjunction that we have from the sum. Now we call an element quantifier free if all of its reindexings are quantifier splittings. And we say that the fibration has enough quantifier free objects if every element in the fibers in any fiber can be covered by a quantifier free object, meaning it arises as the co-Cartesian transport of such an element. Sorry, Ivan, how am I doing with time?
You are doing pretty fine. I mean, this is not up to me to say, but you have 7 minutes. Okay,
thank you. Okay, one of the first things we can do with this is we can characterize completions in the following way, namely a fibration is an instant. I mean, a fibration is an instance of a coproduct completion. So a fibration is a family construction if and only if it has enough quantifier-free elements. So that's kind of a nice result, I think, because it speaks to the naturality of these quantifier or prime elements. And there is another nice story here that generalizes this previous work by Maietti, Pasquali, and Rossolini, and also Maietti and Trotta, that have to do with these Hilbert epsilon and tau operators. So in Hilbert epsilon and tau calculus, one kind of makes, one eliminates quantifies by making them effective by introducing epsilon for the existential quantification and tau for the universal quantification. And this has a fibrational picture. So we call a Hilbert epsilon fibration a fibration such that it has fibered coproducts. The base should have dependent coproducts with respect to the display map category, and every object. So we have the strong condition that every object is actually a quantifier-free object. So it's not just that we have enough, but every object is actually such a guy. And there's a stronger internal characterization, kind of similar to the condition that I introduced earlier, that I will skip for now. But as a corollary, we actually get a family of vertical isomorphisms like this, and those exactly show that that every formula or every element that is the co-Cartesian transport, so every formula of the form exists X such that AX is vertically isomorphic to the reindexing of alpha after the epsilon operator. So these Hilbert epsilon fibrations actually admit a Hilbert operator in that sense. And all of this dualizes to tau operators and fibered products. And one can argue that these fibrations are actually the idempotent algebras for the sigma and the completion respectively. So they are the ones where if you try to complete them, you just get the fibration back. So on our way to the Dialectica principle for fibrations, we want to recover the Skolem principle, which says that we can make universal quantification effective by introducing a higher order witness as a function. So we have this condition of being a local Skolem fibration. So the base has to have dependent products. The fibration has to be bicomplete. It has to have enough coproduct quantifier-free elements, and the coproduct quantifier-free elements have to be stable under products. And from this, we can show that we get kind of point-wisely these Skolem isomorphisms. So that's something that it would be nice to have in a completely uniform way. And I think in the Dialectica case that I'm about to get to, we actually have this, but in this more general locally Skolem case, we don't. So for the condition of Gödel fibration, we have to add this prenixation condition, which can be captured by saying we have a local Skolem fibration, I should say, such that its subfibration of the coproduct quantifier-free elements has enough product quantifier-free objects. And this generalizes the previous result by Davide, Matteo, and Valeria as follows. Namely, we have shown that assume we have a bicomplete fibration, then it is equivalent for this to be an instance of the Dialectica construction, and we can actually effectively construct it. This is equivalent to being a Gödel fibration in the sense that I just outlined. And the key ingredients here, next to our internal characterization of the sigma and the pi completion, is the characterization of the quantifier-free, the sum quantifier-free objects in the sum completion. Namely, those are up to isomorphisms, the kind of constant elements, which are the ones that whose arrow part is just given. So remember, we're looking at the family fibration, which is this arrows in the base together with elements in the fiber of the domain, and maybe the constant elements are exactly the quantifier-free ones, the sum quantifier-free ones, where the arrow is just the identity. And an arbitrary element is covered by such an element because it readily arises as the co-Cartesian transport, because that's just given by post-composition. Yeah, but it takes some time to show that those elements actually satisfy this universal property. So those are the key ingredients. So here I'm pointing out some of the kind of classical and maybe more recent references. So a lot of what we're doing is really a dependent and display map category generalization of this work here. But it's also a fibrational characterization of the epsilon tau operators in the doctrinal case considered by Maietti and Trotta right here. And with this, I'm concluding and say mille grazie.
Thank you, Jonathan, for your talk, and you were absolutely on time. And so thank you very much. And now we move to the question time. So if someone has a question, they can just unmute themselves and ask. So while people think about it, I actually do have a question concerning the local Skolem fibrations.
Mm-hmm.
I wanted to ask you whether in this characterization, did you actually think about whether this could be a completion process? Like there could be a KZ monad whose algebras are precisely local Skolem fibrations? In the spirit of
Yes. Yeah, I think So yeah, I think it's some. So I didn't think about this question too much. Maybe Davide had some more thought on this, but I don't want to throw anyone under the bus. It would be good to know. I agree. Yeah. But there's something. I remember there was something subtle going on that doesn't make it so obvious. Like if they should be exactly algebras. Yeah.
Like from the way you present it, I don't know if someone want to chime in. Maybe maybe it's not exactly like they're more projective objects with respect to some class of maps more than like it's not a completion in the sense of a free completion. It's more some kind of structure more than property, but yeah, whatever.
Yeah, I agree. Yeah.
I see Greta is raising the hand, so Greta, please.
Yeah, this is not to answer, just to ask another question, but which is probably a bit more kind of from the human people side of things, right? So I was curious, maybe you said something at some point, but what do you think was the hardest, like technical difficulty going from the non-dependent to the dependent case, in your opinion? Like where does it get bad?
So getting this to work, that kind of took me at least quite a while to really figure out. I think because I think this has been looked at in the doctrinal case, and somehow there it's I think you get from what I understand, I think you get a nicer result there because it's all post-settle and there's fewer problems there. And it's not even conceptually so difficult, but it was technically kind of ambitious. So that took some time to work out, for sure. And and then let me see. So I think also kind of proving. So I mean So this is fairly straightforward, but then showing that those actually satisfy the universal property, that also the analysis in general of this completion in terms of these quantifier-free elements, that was also something that was definitely doable, but took some thinking also, if that makes sense.
May I ask a question also? I would like to ask you about examples you have in mind with epsilon tau, but not only that, but also the syntactical applications of this or a syntactic calculus or syntactic application to some dependent type theories, or have you in mind some syntactic example beside a non-syntactic one?
Yeah, so I personally haven't thought about this, but I agree that it would be nice to maybe if you think about this in terms of comprehension, or you think about some connection or maybe some subclasses of comprehension categories, that could be a nice way of applying these results to type theory. But we haven't thought about this yet. But I think we're also happy about all kinds of suggestions of applications to people. So,
but what is your best examples? What is your guiding intuitive examples besides the Gödel doctrines?
Well,
one?
Come again, sorry.
What is your intended leading, guiding examples of fibrations, Gödel fibration, which are not reduced to dialectica Gödel doctrines, which is not reduced to the syntactic examples?
I mean, you can always start with the codomain fibration, for instance. I mean, you can argue then. You can argue that okay, then you just get kind of, I don't know, some version of the classical dependent Dialectica fibration that way. So I don't really have anything concrete beyond that, but yeah, but maybe there is something that people secretly have been caring about, which this would give some insight to.
Also having a type theory with epsilon and
Millie, I'm sorry, I have to moderate you because we have to move to the next talk. I'm sorry. So on this, I thank Jonathan for the last time. Thank you, Jonathan, and again, apologies to Millie. Thank you, Jonathan, for your nice talk. And now
Thank you. Thanks for having me.